Vamos fazer a pergunta antes. Se importa que eu hable em inglês? Não? Não é problema? Não, tranquilo. Ok, perfeito.
Bueno, it's a great pleasure to me introduce Mateus Sousa. Mateus is a postdoc student here in the Universidad de Buenos Aires and finished your PhD in Brazil in the Instituto de Matemática Pura Aplicada. And today Mateus will talk about some inequalities in the interface between harmonic analysis and differential equations. Thank you, Mateus.
Okay, so to start, I'd like to thank João for the kind invitation to participate here. So as he said, I finished my PhD in December, like last year, and just started my postdoc here. And I'm under the harmonic analysis group. So officially, I'm not a PhD person, but those are two fields that are very deeply related. I shouldn't say very deeply, but anyway. So I chose a topic that I feel that has connections to both harmonic analysis and PhD, and I chose this fancy name here, but is it working? I chose this fancy name here, but maybe I should have called this Strickland's inequalities and applications. Okay, so I should mention that everything I'm going to talk today, besides the history of the problems, is based on this work, which I did with Hermano Arcanero, which was my advisor, and Diogo Oliveira Silva from the University of Bonn. But okay, so since I don't want to bore you and make you sleep, I may not talk all the details. Okay, so I may tell you some white lies during this presentation. Okay, so today I want to talk about this operator here. So you give me a subset of RD, okay, and a measure that is supported in that subset. Okay, so I have S and have sigma. That's the two things are given a priori. What's happening? Okay. and given a function f, you define this operator T of f in a point C that is in RD. So this inner product makes sense. And it's just the integral of f against this measure and multiplied by this exponential here. Okay? And the S here is kind of redundant because this measure is supported in S. Okay? But this is just so you understand that there is a pair S and there is a measure sigma. Okay? And today I'm going to basically talk about sharp inequalities related to those operators. And by that, I mean that you give me a functional inequality associated to this guy, like, I don't know, maybe an LQ estimate, and I want to know what's the norm of this operator. Like, this is a linear operator. I mean, this is defined only formally, okay? I didn't tell you what is the f that makes this thing make sense and whatever, but this should be linear. It's just an integral of a function against some measure. And I want to know what's the norm of this operator in a certain given two Banner spaces. And I want to know which functions extremize this thing, which functions attain the norm. And also, I want to understand what happens with like extremizing sequences. You give me a sequence that gets closer and closer to the norm. I want to know what's the behavior and stuff like this. So basically, this is the kind of question we are going to talk today. Okay? So sharp questions. And so if you are familiar, in the case where this set S is just the whole RD, and this is sigma is the Lebesgue measure, this is just a Fourier transform. Okay? So this is basically a generalization of the Fourier transform. And I chose this normalization here because there are some sharp constants in the problem, and depending on how you normalize them, everything changes. So I can state the results properly. I put this. I didn't put the 2 pi I here, although I prefer the 2 pi I. But people prefer this in this part of harmonic analysis. Okay, so this is a generalization of the Fourier transform, and although it will be useful today, it's not the focus. I want to study cases where S is actually a singular set. It's like a sphere, a surface, something that has measure 0 with respect to Lebesgue measure, so it becomes more interesting. Okay? But you could talk with, like, you could put here a ball if you wanted, and the Lebesgue measure or some weighted thing, whatever. This always makes sense. Of course, you have to ask when this is well defined. Anyway, so again, I want to study things like this where S is a set and sigma is a measure. But why did these guys come up in a PhD seminar? So first, one of the oldest cases that people studied was when S is equal to this set here, which is the paraboloid. It's functions that are equal to something on the first entry and the module squared on the second one. So this is just a paraboloid, okay, but in RD. And I'm taking sigma to be this measure here, this delta of t minus x squared just tells you that this is 0 outside of the support of the paraboloid, okay? And this is just a projection measure of this guy. So this is just RD, but lifted to a surface. This is just a graph of something. So if I want to measure a set here, just project it and see the measure on the projection. So in this case, the operator is going to look like this, okay? So the paraboloid is in RD plus 1, because we have another coordinate here. And you have this operator in two coordinates, one in RD and one in time, one in a real value. So it looks like this. And I put RD here. I should have put in like f of x, x squared, but you can identify functions on the paraboloid with functions on RD. In this case, this is obviously the solution to the Schrodinger equation, right? Right? Everybody can see that? No? Okay, so in case it's not so obvious to you, let's take a look and let's do something very slowly now. So I have an operator defined in terms of this function f, and I'm telling you that if I think of this as a space and time variable, I can write this as a solution of a differential equation. Okay, so let's see if this checks the differential equation, right? First of all, you have to check this, okay? So when you put 0 here, tau equals 0, this dies. So there is no x squared. It's just a Fourier transform of something. But it's in some sense it should be okay, here I should have like an inverted hat. Okay, so it's not completely true, but okay. And so we have to test this. Okay, so let's differentiate the operator in time. So if you differentiate this in time, you get this. F of x e ix squared just this. That whatever was over this exponential just falls. So you have this guy here, and then I multiply both sides by I, and you get this. Minus x squared f of x e to the ix xi e to the I xi squared tau. Yes. Okay? But for those of you who understand a little about the Fourier transform, this guy here, if you have an x squared multiplying a function, this is just the Laplacian. You have to multiply by 2 pi d here. But this is basically the Laplacian of f hat inverted. Okay? And then you can just pass the hat to the other side. And you get a Laplacian of f hat e of x multiplied by the whatever is here. So you have a Fourier transform of something. Okay? But this factor here is just on the Fourier side is going to just give you a translation. It's a multiplication by a ei something factor. And this side here is a function. It's a g of x. So this is going to be g hat of x minus c. So this, I'm going to erase this. So this is just a convolution. This is 2 pi d convolution of this guy with a function g on c, evaluated on this point, if you wish. Maybe there was maybe here is equal to this. Okay? So you have a Laplacian convolved with something, but convolution is a nice thing. You can take the Laplacian out. This is just 2 pi d Laplacian of the convolution. And then you can redo everything, and the Laplacian is now out, and then you get just Laplacian 2 pi d. And then, okay, so when you invert, you're going to have you have to kill this 2 pi d on the other side, and you get the Laplacian of u on the variable x. I'm excited. Here's a function of tau. So nice. So this operator, that is just a Fourier transform of something, in some sense, gives you the solution to this equation. Okay? And I chose f in L2 here because in L2 the Fourier transform is a isometry. So and is a unitary operator. So any function in L2 is the Fourier transform of something. In particular, is the Fourier transform of something times a constant. So basically, every solution to this equation when the initial condition is L2 is given by some integral like this. So I have this operator that a priori has nothing to do with equations, but gives you a solution to this particular differential equation, which is the Schrodinger equation. So I could just drop this 2 pi d f hat here and just put a function g, if I wish. Usually when you are working with PD, people just divide here by 1 over 2 pi d and plug the Fourier transform here. Okay? So this is called the Schrodinger propagator. And if you ever took a spectral theory course, this is just the flow associated to the exponential of the Laplacian. Okay, so but this is just an explicit formula. Of course, this only makes sense if this is actually integrable. So what people do is you define this for Schwartz functions if you want, and then you extend it by density after you prove some estimate. Okay. Okay, so an operator that is in some way a generalization of the Fourier transform, and it gives you a solution to a PD. But this is not an isolated phenomenon. Okay. Same thing happens if you take the cone. Okay, so just x on the first coordinate and mod of x in the second one. And I plug this measure here. Okay? Same thing, it's a measure that is supported on the cone, but it's normalized by t. I'll tell you in a moment why it's normalized by t. But the thing is, you can redo the same calculation, and if you erase this square here, and you put a x, when you differentiate twice, you're going to get the x square you wanted. Sorry. But to get the x square, which is the Laplacian, you have to differentiate 2 times. So you're going to get something that like the second derivative in time is equal to the Laplacian in space. So this is where the wave equation comes from. And of course, you have to, the initial condition and the initial derivative have to be well defined. Same thing happens with other surfaces. The sphere, it generates solutions to the Helmholtz equation, which I'm not going to define here, but if you know it, very nice for you. And if you take the twisted paraboloid, which is just a paraboloid on one side, and I should say twisted parabola here, actually, because this is just in R2. And if you, so it's a paraboloid on one side, on the other side is just the same thing but twisted. And this generates solutions to the so-called Benjamin-Ono equation. And if you do the same thing with this cubic surface here, it gives you a solution to Airy's equation, or some people call it KdV equation, or linearized KdV equation. So basically, every time you have a rational function of the modulus, if it's to a I don't know, rational power or something, you can come up with an equation. But these are some very important cases. Most of these, like those 3 here, the wave equation, Benjamin-Ono, and Airy's equation, they all, in some way, they model some sort of behavior of waves. This is like short waves that go for very long. The other one is general waves. And I don't remember what Benjamin-Ono models, but it's also no wave. And Helmholtz equation is the eigenfunctions of the Laplacian. Okay? So I hope with this, I convince you that this whole thing is connected to PD. Okay? Any questions so far? No? Okay, so let's move on. So okay, so the thing is, if there is a duality, you give me an operator, and if I have some estimative for this operator, it's going to give me a space-time control of the solution. In what sense I mean? For instance, for the paraboloid, it is known that this is true. If I start with a function L2 of Rd, which I can think of as L2 of the paraboloid, okay, this gives you a function that is in Lp of Rd plus 1, where p is given by this. Okay, it depends on the dimension. But it's a number that is bigger than 2. It's 2 plus something. Goes to 2 and d goes to infinity, but it's always bigger. So this tells you that if you start with an L2 function, it ends up in a better LP, in both space and time. So it says that for almost every time, for instance, if you apply Fubini's theorem, it tells you that for almost every time, this function here is integrable with respect to the variable x, if you fix a time. This is slightly better than what you get just by using the flow. Because the unitary operator that was defined in the beginning, I told you, is just the flow of the Laplacian, the e to the I Laplacian, t. It tells you that in every time you have a function L2, and it's a unitary operator. You learned this in spectral theory, for instance. This tells you that it's also in a bigger LP. So it gives you more integrability, but also gives you a control in space and time. Or if you can think in this way. So you give me a function u that is a solution to the Schrodinger equation, and you have u in space and time, and it's controlled by the L2 norm of the initial condition. Okay? So this is for the paraboloid. For the wave, in general, it's the paradigm is true, but sometimes you have to change this L2 here for some Sobolev space. Okay? Because I defined, okay, so here, for instance, I defined this divided by t. Okay, but t is equal to mod x, so this is actually just dividing by mod x. And this is going to generate a h1 half. Yeah, believe me. So this is what happened for the cone, for instance. You can rewrite everything. You can calculate the solution explicitly. It's given in terms of this operator, of the one associated to the cone, and it gives you this inequality. Okay? That the function, the solution to the equation in space and time, is controlled by the h1 half norm of the initial condition, plus the h1 minus 1 half norm of the initial condition, the derivative of the initial condition in time. Okay? And this 1 half and minus 1 half is expected because here I differentiate one time, so you should drop at least once. So there is a 1 difference here. But here the exponent is different, okay? It is slightly bigger than this one. Okay, you have d, and here you have d minus 1 dividing. So this is better with dimension. But it doesn't work for dimension 1. So in the case where the cone is just 2 lines, this doesn't work. I'm not going to go into details today, but this happens because for these things for you to have one estimate like this, the surface that is associated has to have curvature in some direction. Okay, so there is always also the duality is you have an equation, you have a surface, and one estimate for one side gives you something for the other. Okay? Okay. So, but today I want to talk about this specific case. So I told you about the paraboloid and the cone and some other things. And I want to talk about this guy here, the hyperboloid, which is given by this. Okay, so the second coordinate is equal to the square root of 1 plus the other one. This is just one sheet of the hyperboloid, right? Usually you define hyperboloids as something that has 2 sheets, or it's rotated around one axis. In the bigger dimensions, there are many more hyperboloids than you have in dimension 2. But I'm just taking the upper sheet of the hyperboloid. And this is the measure, okay? So it's supported on the hyperboloid, and it's divided by this factor. Okay? This is, if I change this 1 here by some number, okay, by a lambda, if I send lambda to 0, this is going to look like a cone, because you're going to have the square root of the mod of x squared. And the same thing happens with the measure. If I divide by lambda here. So this is, the cone and the hyperboloid have this thing in common. This is the measure that should be here, in some sense. It's called the Lorentz invariant measure. Okay? And so the operator, when you write it, it's going to be like this. Same thing, okay? So it's f times some exponential times the measure. So I write everything down, it becomes something like this. It's slightly uglier than the one I wrote on the first slide, but it's still writable in one line. And for this to make sense, f has to be in some appropriate class, right? This has to be integral. Okay? And so the thing is, people have studied these surfaces for a long time, and in particular this case, there is a classical work of Strickers that tells you if you start in L2 of the measure I defined it on the other slide, you end up in LP, and the P is given by this interval. Okay, I'm going to write this down because I want to remember this. Okay, so let me write three cases here. So I have the paraboloid, cone, and hyperboloid. So here, P is equal to 2 plus 4 over d minus 1. Here, 2 plus 4 over d. And here, it is in between 6 and infinity for d equal 1. And 2 plus 4 over d, 2 plus. Okay? So remember this interval. This is going to be important in the future. Yes, I'm going to get there in 2 slides. But I wrote this down because the hyperboloid is the thing in green. Can you tell the difference between these colors, by the way? This one is in green. This one is orange. And this one is blue. Blue is the cone, just a section, of course. And this is the paraboloid. And the reason why you have this interval here is sort of because this is trapped between the two surfaces, okay? Of course, this needs more work than what I'm telling you here, but this is more or less the reason. Like when you're close to 0, to the vertex of this thing, this looks like a paraboloid, but on infinity, that you have asymptotics, asymptotas, I don't know, that converge to a cone, to the cone, okay? And the paraboloid is going to be this guy here. But of course, I defined the paraboloid with x squared, but you can divide by anything, it doesn't change. You just dilate everything, it's the same. Okay, so I want to talk what is in between. In fact, you can actually do the opposite. If you have something for the hyperboloid, you can prove something for the cone and the parabola. So they are equivalent. But this is very technical, so I don't want to do this today. But okay, so this is the equation. This is called the Klein-Gordon equation. So remember the wave equation, which was like two differentiate in time, differentiate 2 times in time, twice in time, and equals to Laplacian, would be the wave equation. And I'm adding this factor here. So this is where the 1 plus x squared comes from. Okay, so you have this guy here, and it should come from here, from adding this thing. And you can actually multiply this by a lambda, and it's going to give you all the other hyperboloids, the ones I didn't define here. So it looks very much like a wave equation, right? And the same way that I did before, the operator, this guy here called Klein-Gordon Propagator, which is just the group that are generated by the exponential of this square root of 1 minus Laplacian. Instead of Laplacian, now you put the square root of 1 minus Laplacian. Okay, this is a positive operator, so this makes sense in some way. So you have this guy, and the solution to this equation can be written like this. You have to do combinations of the first condition, the second condition. For people who are doing differential equations this semester, think of this as an ODE, okay? So you'd have something linear here, and you have the second derivative in time. This should be something like a sine plus a cosine, and you have combinations. If you look, you have it something, I minus it something. So this is just a sine of the square root of the Laplacian multiplied by the first condition. And the other one is this is the cosine. The other one is going to be the sine divided by square root of the thing. So if you remember the equation, I don't know, think about the ODE. If you have 2 times the derivative in time equals something of u, this is going to be a combination of sines and cosines multiplied by the initial condition. And that's exactly how you get this. You pass to the Fourier side, and this becomes an ODE, and you just do calculations. Okay? And of course, if you think about the operator that is associated to the hyperboloids, this is the relation. Okay? So T of f, if you choose f to be equal to this thing here, is equal to this thing here. Okay? So one side you have the operator, on the other side you have the propagator, the exponential of this thing. Okay? So in this particular case, this gives birth to 2 estimates. This one, which I already wrote down and even gave you the range of exponents, and this other one here, which is a Sobolev estimate. Okay, so this side here is much more geometrical, and this side here is much more analytic in some sense. You have a functional space here that has to do with derivatives, and it's the favorite space of all people that do PD. Maybe not this H1 half, but some HS. Everyone has its own favorite Sobolev space, right? And the thing is, although those two inequalities are equivalent, in the sense that this one is just a rewriting of this one. Okay, so you choose this guy here, and it's the same. And the constant relates like this. Okay? So I told you that I wanted to ask questions about sharp constants, so I have to be careful with factors. So you have 2 pi d. And although this is just a constant, if you wanted to do things for every dimension, you have to look that this goes to 0, and with the dimension. And I have a funny story. I was writing a paper a few months ago, and we missed out some 2 pi d, and we lost 2 days doing calculations because for some reason 1 was going to 0 exponentially fast. And that was exactly because we lost some 2 pi minus g somewhere. And so this is sometimes a kind of a bitch. But anyway, again, I want to do sharp versions of those things. Okay? And today in particular, I want to do things for the hyperboloid. So I want to answer this question. What is the value of this guy? Okay? Ideally, I want to know this for every d and every p that is here. Okay? Ideally, but you'll see what happens. And so not only I want to know the value of these constants, I want to know who are the extremizers, if they exist, and what happens with extremizing sequence. Okay? And okay, so far so good? Everybody holding the wheel to sleep? Okay, so let's move on. So of course I'm not the first person to do this. Okay, this problem has a history. It started more or less in 2003 with the work of Mario Kunze, and people kind of understand everything that happens with the paraboloid. They know that Gaussians, remember the paraboloid is just RD. You project everything, you can think of RD. All the surfaces are equal to RD. They're just graphs. Okay, so you can forget the surface for a moment when you want to know the extremizers and think of functions in RD. And in the paraboloid case, Gaussians are the extremizers. Okay, but only when you have an even exponent. Okay, so you have this thing here, which is 2 plus 4 over d. And this is not even for a long time, right? Because 4 over d goes to 0. So this is 2 comma something after a while. So it's only even when d is equal to 1 and 2, unfortunately. So people only know who are the extremizers for dimensions 1 and 2. But on the other dimensions, they know that extremizers exist. And I think they know the extremizers also is smooth. So this is all done by considering Euler-Lagrange equations and stuff like this when you don't have other arguments. For the cones, same thing is known. Like for low dimensions, exponential functions are the extremizer. So here Gaussian is an exponential of minus x squared, and here the exponential is e to the minus x, which is kind of adapted to the surface, right? One is associated to mod of x, the other one is mod of x squared. There should be some connection. I still don't completely understand what happens here, but there's this nice coincidence. Same thing. People only know this for the case when you have even exponents. But they know that there are extremizers in every dimension. Okay? This was done by those people. And there's the sphere. The sphere is more or less, is the oldest case. I mean, of course, if I ask you, tell me one set in RD that has measure 0. And I think the first thing that comes to mind of everybody is the sphere. Like, it's the simplest case that is not RD. And I gave you paraboloids and cone and everything because the people from dispersive PDE were very interested in these at more or less at the same time that the interest in the sphere came up. But, okay, so the good thing is the sphere has the same exponents as the paraboloid. But if you consider the sphere with surface measure, okay, it's a probability measure, or I don't know, finite measure if you want. So you also have the L2, L infinity, always. Every time you have a function L2, you integrate against an exponential over a finite measure. This is a bounded function. So you not only have this, but you have everything up to infinity. So you have a range of exponents that is always unbounded in every dimension. So people sometimes ask what happened on outside of the endpoints. But people only know that for the endpoint case, which are more interesting in some sense, people only know what happens for the 2 sphere. So S2. And they don't know who are the extremizers for the circle. So this is a kind of a pathology. So you know something for the 2-dimensional sphere, but the circle is still an open problem. But it has been studied, and some very good mathematicians have tried to solve this, but still, there are some conditional results, like comparison principles and stuff like this. But people still don't know what happens to the circle completely. But every time I gave you something that was L2, LP, okay? But of course you can think of LP, LQ, always. And you can also think of cases that are not isotropic. You can put like mixed norms on the other side. People have asked this question as well. In the case of the sphere, for instance, people have been interested in this operator with this set of spaces, like leaving L2 and going to something that is, you integrate on the sphere with respect to the angle in L2, and then you just integrate on the radius with LP. And you multiply by R d minus 1, elevated to d minus 1. So this looks like the integration in polar coordinates. Okay? For this case, which is not which is not the hardest one, because in some sense this is weaker, because just by using Holder's inequality inside, you can get to the full LP. But for this case, it is known that every time you have an even exponent, which are many, because as I told you, it goes from p to infinity. So every time you have a mixed inequality and you have an even exponent, constants are the unique extremizers. This was part of my thesis. And also, we actually managed to show that after a while, like for big P, if you take P like after something that depends on the dimension, it's also true that constants are the unique extremizers. Okay? I don't want to do this today, but that we know explicitly what is the value of after something. We know what is something. It's actually for a while I thought about talking about this because also we had some numerics here, so I could talk about the other half of the seminar, right? This is PDE and numerics, but I only realized it this morning, and I already had prepared the slides. So. Okay, so paraboloid, cone, and sphere, and the hyperboloid is what I'm going to talk today. And now after this, I'm going to tell you that we know that all the even exponents that are endpoints will not have extremizers in low dimensions, but something different is going to happen. Okay, so these slides are going to be available on the web page of the math department, I think. So if you want, you can look at this survey here. It's from last year. It is very, very up to date, but some stuff has happened since this was published, but it's kind of very, it's updated enough. Okay. Okay. So what happens with the hyperboloid? So the first guy who worked on this was Henrik Lodran, and he studied those cases: 2, 4, 2, 6, and 3, 4. Okay. Here's the dimension. Here's the exponent. So let me write down the. Okay. So I want to erase this. Okay, so dimension 1, you have something, this is the interval. It's from 6 to infinity. D equals 2, it's in between 4 and 6. I should write the 4. 4 and 6. Closed. Okay? It's closed here, and it's open on infinity. For dimension 3, here's a 6, okay? It is something that looks like this. It should be 10/3 and 4. And this goes moving on to the closer and closer to 2. The thing is, after dimension 3, the exponent on the upper endpoint is going to be 10/3. It's always the one on the other dimension, okay? It's going to be 10/3, and it's not even anymore, okay? So those 4 cases, these, and these, are the only ones where you have an endpoint and it's even, okay? So there are only 4 cases, and Kilodran did 3, and he calculated what was the value, but surprisingly, there were no extremizers. This came as a surprise to me because when I started studying this, in many cases there were no extremizers, but every time this happened, you had some very strange surface, like a perturbation of things. And this hyperboloid or cone or paraboloid, they are more or less like homogeneous. And this shouldn't happen in my opinion when I started looking at this, but I didn't understand completely what was happening. But anyway, in these cases, he solved this part here. So those 3 endpoints are even. Okay? So this is the observation. These are the only ones where D is bigger than 2 and P is an even integer. But he left open the question of what happens when D is equal to 1. Okay? So you only have one endpoint, is the lower one, and it's 6, which is an even exponent, which you're going to see in 5 minutes why even exponents is important. But when this problem came to my attention, I thought, okay, you have 6, but you also have what else? You have 8, you have 10, you have 12. So it was paradise, right? You have an infinite number of even exponents. I thought, hey, let's try to do them all. Yeah. Okay, so we did the case P equals 6. And we proved the same thing, okay? We calculated the sharp constant, and we proved that there are no extremizers in this case. So consistent, right? Okay, so what was known was that there were no extremizers and people knew the sharp constant. And we thought that this should be the case for all the other cases. Like for 8, 10, and 12. This should be the theorem. We wanted to find out what was the sharp constant and tell people, no, there are no extremizers. Unfortunately, that is false. If you are in between the endpoints, there are extremizers. This was interesting for me at the time because it provided like different phenomena. So you have a surface where in some cases you don't have extremizers, but in others you have, and this happens more or less because you don't have the dilation symmetry. So this here completes the this completes the picture of what happens in low dimensions for the hyperboloid. So people knew what happened to the paraboloid and the cone, which were like the extreme cases, and we did the rest. Like the hyperboloid was everything in between. And I want to talk about this for the next 10 minutes. Okay. So why even exponent is important? Okay, let's do a case. So imagine you have L6. Okay, L6 in R2. Okay, so this is an L6 norm. You can write this as the L2 norm of a cube. Okay, very simple. But this is a Fourier transform of something. I wrote this as an operator with integral blah blah, but you can actually think of this as a Fourier transform of a measure, which is f times the measure, and this is a temporal distribution, or whatever that is. And you can think of this as a Fourier transform in the distribution sense. So if f is nice enough, this is a convolution of 3 measures, and it's the Fourier transform of the convolution of 3 measures. But the thing is, if you have a distribution that is whose Fourier transform is in L2, that function is also in L2. It doesn't have to be a function. This is a distribution, it's a measure, and you are taking the Fourier transform, and here you have a Fourier transform of something that is in L2, and I can just invert it. Okay? So here on this side you have something that is an oscillatory integral. Okay? It's a function against an exponential, blah blah. On this side you have a convolution. But this is for people who like additive combinatorics, and then they see the connection between Fourier analysis and combinatorics. This side you are studying sums of things, because convolutions is just summing, like summing points in some sense. And this side is you are summing exponentials. And multiplying exponentials in some sense. So this is how sometimes people see Planck arrows with convolution and products. This connection here is exploited very much when people study combinatorics. It's I don't know if you want to ask more. I'm not a specialist on this, but there is a guy who is always like visiting this university, Pablo Shimerkin, who works a lot on this thing. Okay, so not something very deep, but just a comment. So in this case, if I want to calculate the sharp constant, was the supremum of this guy over the L2 norm of something, I can just pass to this side. What is the advantage here? Here I had an oscillatory operator. Here everything is positive, in the sense that if I grab a positive function f, this is going to be a positive function. Okay? So now I forget all the oscillation and change the problem to studying convolutions. So this is why, of course I choose 6 here, but I could put any even number. Okay? And you would get a multilinear thing on one side, and you have an L2k norm here would give you a k linear thing. So that's why people sometimes can do the even exponent cases for this in this setting. Okay? Because you can change Fourier transform for convolution. This is actually very common when people are studying sharp inequalities related to Fourier transform, because there is this duality. So if you have an even exponent, you can change the problem to something that is not oscillatory anymore. But don't fool yourselves. Okay? So this is just a simplification in some sense, but this problem is equivalently harder to this one. For instance, the case of the circle is not done, and you can do the same thing here. You can do the simplification. But this is just the first step. I change the problem, and I'll try to do the other one. But there is a technique that kind of is the first step to try to tackle this problem, and which is called delta calculus, which is some fancy name for using co-area and in a very smart way. This was introduced by this guy, Damiano Foschi, who studied with Sergio Kleinerman, and Kleinerman kind of uses this thing a lot in some of his research. I don't know exactly why, but what research actually, but I was told by him that he learned this from Kleinemann, which learned this from Hormander's book. Which book, I don't know. There are 4, right? Okay, so how do you do this? I don't want to do any details because I don't have time for that. So I'm just going to give you the highlights. So what people do is that after you have this convolution, you can sort of Cauchy-Schwarz. Okay? You do, this can be written. Like you can do some calculations and you can prove this thing here. Is L2 norm? Is it smaller than something like this? A product of 6 variables. Of something that depends on of a vector here, which I'm not going to tell what it is. dx1, dx6 in this case. Here is g of x. I'm going to write this as g of x of this big vector here, okay? So you can work and prove something like this. And then what you do is you have a function that depends on, okay, so this g of x is actually very explicitly. G of x is just the sum of the first 3 minus the final 3. So what you do is this is actually an equality. Sorry. This is an equality. So what you do is you do Cauchy-Schwarz. So to go from here to here is where the data calculus comes into play. So I don't want to do this. But once you have this, what can you do? You can do Cauchy-Schwarz with the following 2 functions. You just take f x1 times f x2 times f x3 times the square root of this thing, and you take the other 3 times the square root of this thing. Okay? So when you do this, you're going to get an integral. You're going to get the same integral, okay, 2 times. Because you're going to have the first one with x1, x2, x3, and the second one with x1, x4, x5, x6. And then you calculate something here, and then you are done. Actually, this is slightly false. This is a different function here. Not. So you do Cauchy-Schwarz and you get something like f square, and you get here sigma of x1 plus x2 plus x3. Sorry, that is what happens. So usually this step here, it gives you a functional equation, and you just did Cauchy-Schwarz, so you know when Cauchy-Schwarz is sharp, right? If you have a equality in Cauchy-Schwarz, you know that one function is parallel to the other, then it gives you a functional equation. And then you solve the functional equation, and this gives you one condition for equality. And then you have to study this convolution here, sigma, convolution, sigma, convolution, sigma. And if you prove some nice properties, then you can kind of put this out, and then you have to study when you have equality in each case. This was nice because the first time this happened, it was the paper by Foskey, the initial one. He got very lucky, and sigma was constant. So you just dropped this out and you were done. You just had to solve one Cauchy-Schwarz. Of course, this doesn't happen all the time. This happened in this one case, and for the other cases, you had to work a little more. Okay, so you do this, and usually if it's not constant, you have to localize the maximum and study what happens. And of course, the maximum here is going to give you a candidate of a sharp constant. And if it is the sharp constant, you have to localize around it. Okay? So in our case, the maximum was supported in a set of measure 0. So that's why there was no extremizer. So you could not localize it in some sense. Okay, so this is the outline of what you have to do to calculate the sharp constants and prove that there are no extremizers or that there are extremizers. But of course there are many. Okay, so one step is trivial, but this doesn't work all the time. For the sphere case, for instance, there was a magical identity here that Foskey introduced, which worked. So this happens differently. The way you Cauchy-Schwarz is important, and people don't have a general mechanism to solve this yet. Anyway, for the case of existence, it's for people who know concentration compactness. It's basically that. Okay, so I told you the existence thing was not on the endpoint, so this gives you some room to interpolate things, and you can apply this technique of concentration compactness, which was something that was introduced by Lyons in the 80s, I think. maybe 90s, I don't know. And it basically, you have to analyze when there is mass concentration in a point or at infinity, or you have to rule it out for a sequence or for an extremizing sequence. Okay? And I'm not going to tell you the details, but the hard part is usually proving that you have an extremizing sequence in L2. So L2 is weakly compact. So you already have a candidate for extremizer. Okay? The problem is that there are many symmetries here. So you could screw up the sequence in many different ways. So the compactness has to be up to symmetries. You have to adjust everything so the mass doesn't escape to infinity. And after that, you have to prove that your sequence doesn't converge to 0. And that's the hard part, as is in many cases when you are in infinite dimension. And for that, we prove that there is basically a set, which you have positive mass of every function on the sequence in that set, after moving things around. So in the case of the 1D setting, what we do, we take the hyperbola, we divide it into pieces, like you have red and blue, red and blue, red and blue. This is just intervals. And they all have the same measure, okay? That normalized measure, square root of 1 plus x squared. And the thing is, there is a transformation that changes everything to the origin. And you can sort of move things around and prove that they concentrate on the origin. This is very technical, but I don't want to do this today. In dimension 2 is slightly worse, because you don't have such a nice decomposition. What we do is, for every dyadic annulus, we divide the annulus that for instance, here is the ball of radius 1. Then it's from 1 to 2, 2 to 4, 4 to 8, 8 to 16. And the number of sectors is equal to the radius, okay? So here you have 16 to the outer radius, okay? And the thing is, although there is no such thing as a nice transformation that is a symmetry of the problem that changes one into the other, you can rotate and do something and everything gonna fall inside the ball. And all those guys have measure that is comparable. So the idea is that you have to prove that if you have an extremizing sequence, that in some of those guys, in at least one of them, all the functions are not, they have positive mass, like bounded by below a universal thing. Okay? So how do you do that? Okay, so since I don't have much time, I'm just going to tell you very quickly. So the thing is, you have to understand, so you have an L6 norm. I'm going to erase this. 2 minutes. This was a decomposition of RD. So what you do is you write T of F as the sum of T of F, characteristic of each of those guys, let's say AK. Okay? And then you want to calculate an L6 norm, or an LP norm if you want. So this is the square root. This is the same thing as this. Okay, here I'm going to do this, which is squared LP over 2. I think it's like this. So you can divide by P for 2 and you get something like this. Nice thing is P is always bigger than 2. So if you divide by 2, it's still bigger than 1. And the idea here is you study what happens with the squares. So, but now if you write this down, you have a square. This is just going to be the product of everything. So this is the bilinear part. And what you have to do is prove something that is better than Holder's inequality. Okay? And then you prove something that is better than Holder in the sense that the constant that is going to appear depends on the interaction. And then you sum everything. And that is going to give you the special set, which are called special caps. And the rest depends on the fact that this is not an endpoint. Okay? So I'm not hoping that you understood these last 3 minutes because it was very quick. But this is just a highlight. So if you want to ask me this later, I can tell you guys. But I hope you got the gist of the ideas. So it's two very different things, those theorems. This guy, this guy. Because, so the thing is, if you want to, there are two different philosophies. If you want to calculate a sharp constant, the best you can do is like prove that for a function to optimize it, it has to have lots of symmetries. And then you do a first symmetry, second symmetry, and then at some point you just end up with a Gaussian, a constant function, something nice. And after you prove that every extremizer has to satisfy this thing, then you end up, and you calculate the sharp constant, because you end up with only one or a family of candidates. That is the wishful thinking, okay? But again, to calculate the optimizer, the sharp constant, the more symmetries you have, the better, because you can do reductions. On the other hand, to prove that a sequence converges, the more symmetries you have, the worse it is, because the sequence can fail to converge in many different ways. So it's two different games here. To prove existence, it's better that it doesn't have many symmetries, and to prove and to calculate things explicitly, you hope that it has many symmetries, or at least that the symmetries that they have simplify things a lot. Like in the paraboloid case, for instance, the symmetry, you do Cauchy-Schwarz twice, and one of them tells you that the function has to be a product, and the other one tells you it has to be radial. So there is only one function that satisfies that. It has to be a Gaussian. And something similar happens to exponentials. And constants, the same thing. You are in the sphere, you prove that the function has to be radial in the sphere. So it has to be constant. And so this is usually the case. But for existence, it's slightly different. Okay, so I hope you liked this exposition. I hope you didn't sleep too much. And thank you.
Thank you, Mateus. Some questions or comments? There's no question. Thanks, Mateus, again.